stay at home all day.
I can't just do that.
Moving for that, home ones.
So there was quantitative analysis. There was
Variable outlines around.
That's what
Oh,
and then multiple choice.
I see that. That makes sense. I just.
Yeah.
It is better.
After.
Yeah. But you have to do the IMAX one, the one that's kind of low volume, right? I get that. All right, so here's the deal. We're gonna go ahead and get started. I think it's worth turning off lights here. Maybe just that one. Is that all right? You guys, we'll see how that goes. All right. So let's go ahead and get started. We are going to do something really cool today, and I put so much into this, I was like, I just kind of want to see where this is going before I make that homework assignment. So I'm going to stay here late tonight, so you'll get your last 2 homework assignments tonight, and then they'll both be due whenever you want. We'll talk more about that later. I haven't talked that far. But I did definitely want to use the time today to talk about Chapter 6. And I'll do a lot of Chapter 6 today, and I will finish Chapter 6 tomorrow, and we'll be into Chapter 7 tomorrow. So just keep reading and reading and reading. Right now we need you really reading more than anything. Okay. So, Chapter 6. Topic is calculus of variations. Okay, so what we're going to be talking about relates to systems where Newtonian, like the Newtonian representation of mechanics is not convenient mathematically. So let's talk about this first in terms of coordinate systems. As you know, we have different coordinate systems that we use for different things. We have the rectangular coordinate systems. And you know, that can be a nice system to work in if, like, let's say you're going to maybe use this room as your frame of reference, because for one thing, in that case, the gravitational force would just be mg to the minus y hat. So we could use that piece of information. But then we also have the spherical coordinate system. And in spherical coordinates, we like to use them whenever we have that spherical symmetry. You can imagine, like, you have a point source of an electric field, something like that. Or if you were going to do something related to gravitation, but you were going to do it far enough from the Earth that you were using that expression for gravity that was the minus r hat. Also, we have cylindrical coordinate systems. Whenever there's axial symmetry, maybe a line of charge or a line of mass involved. And then we have these specialized coordinate systems. And a lot of times, these are most useful whenever we have something like a constraint on our system. So for instance, let's say that your object is moving along an inclined plane. You would say, okay, we make a coordinate system such that along the inclined plane is one axis. Would be the simplest example. But another example might be an Atwood's machine, where a displacement along the line of a string would be the useful coordinate. I'm trying to think of another one. We had the bead that was confined to the wire, where the distance along the length of the wire would have been the useful coordinate. So those types of systems they come up a lot. And in that case, we would like to use these specialized coordinate systems. The problem with using those is purely a mathematical one. The problem is that if we want to use those types of coordinate systems, but we still want to use Newton's second law, we still need to use acceleration in rectangular coordinates. Because we still have this statement of Newton's second law, and that force equals mass times acceleration, which we have to, in order for two vectors to be equal, we express that as the net sum of all x components of forces is mass times x, sum of all y components of forces is mass times ay, the sum of all z components of forces is mass times az. Ultimately, Newton's second law has to be expressed in that rectangular coordinate system. This expression gets very, very messy if we even try to go to spherical and spherical coordinate systems. So, I mean, we've sort of done a good job of not showing you that, but that is the fact. So, when it comes to using other coordinate systems, using Newtonian mechanics is really clunky. So it'd be nice to find something other than Newtonian mechanics that we could apply when we're using one of these specialized coordinate systems. And that alternative would hopefully be equivalent to Newton's second, but it would give us an equation of motion as well that we could solve, but it would work with our new coordinate system. And so that, so let me get that right. So what we're looking for is we're looking for something other than Newton's second law. But hopefully equivalent to it, from which we can get an equation of motion but that works equally well regardless of coordinate system. So, I mean, normally people would stop at this level and say, oh, let's just take these things and try to force them into this rectangular coordinate system and keep using Newton's second. We did that for a very long time. But then we realized, you know what, there might be another way that will work well with these other systems. And of course, there will be another way, and that will lead us to Lagrange's equations. And we'll get to one today. Are you guys okay with that, or is there anything that's not clear? All right. Then let's start by, ultimately, in order to use Lagrange's equations, we will need to convince ourselves of them and prove them. And in order to do that, we are going to have to use the variational principle. So we're going to have to talk about that. That's what this whole chapter is about. You guys already know this stuff. I should start by saying that. How much do you guys already know about variational calculus? That's fine. All right. Okay. So let's start with a couple of examples, just as your author does. All right. So. And these are going to be examples that illustrate problems of variational calculus. So what we're trying to illustrate here is that there's such a thing called the calculus of variations. And that the meaning of that term is usually just finding the minimum or maximum of a quantity that is expressible as an integral. And just to be very clear, the antecedent to the word that is the quantity. The quantity is expressible as an integral. Okay? All right. So, an example of that is the shortest path between 2 points. Okay, so here is the statement of the question. We are given 2 points in a plane, and I'd like to find the shortest path between them. The points are x1, y1, and x2, y2, and the path can be expressed as where y is a function of x that connects them. So what I'd like to know is for which y as a function of x is the path the shortest. Given 2 points, x1, y1, and y2, that can be connected. They are in a plane, I should be clear about that. And the paths are going to be confined to that same plane. So which function, y of x, will minimize the path? So which y of x is the shortest path? Now, that's a pretty, kind of an easy question, because we know the answer will be a straight line. It will be a linear path, because we are in a Euclidean space. You can imagine that in general relativity, this is not an easy question. But for right now, this is an easy question. All right. So let's go ahead then and set up that problem. I'm going to draw a figure. All right, so I've got my x direction, my y direction. I'm going to start here. x1, y1. And wind up here. x2, y2. Okay. And I'm going to imagine just any arbitrary path. All right? And along that path, I'm going to think about, so this is just some path. Along that path, I've got, y will be, y will be a function of x. Okay. So if I take a piece of that path, maybe an infinitesimal piece would be good. In that case, then the increment of length that's associated with that infinitesimal piece, dl, will be, okay, I go over an amount dx and up an amount dy, so that'll be dx squared plus dy squared, quantity square rooted, for that. Where during that infinitesimal increment, I go over an amount dx and up an amount dy. Okay, so now I have, our expression for dl. I also want to point out that this increment dy is equal to the slope, dy dx, times the increment dx. Because that's an infinitesimal displacement, so the slope will be a defined quantity dy dx. All right, so, and I can write that if I like as y prime of x dx. That'll be the writing convention we'll be using for that. Okay. So now, if I want, I can write, oh, and you know what, your author doesn't use dl for that, he uses ds. So I'll use that as well, ds for d length. Because s is used for arc length, and any time it's curved, s is often used. All right, so now for ds, I've got this original expression here. I can make the substitution up here. And I've got y prime x squared dx squared, quantity square rooted. And I can pull the dx squared out, so what I'll have is the square root of 1 minus y prime of x squared. That quantity, by the way, is what's going to be squared in that, times dx. All right. So now, if I want to write an expression for the total length of this path, represented by capital L, where L must be equal to the integral over ds. All right, so from point 1 to point 2, ds. All right, so let me go ahead and make my substitution here. Got square root 1 x squared dx. So dx is my variable, so I need to go from x1 to x2. All right. So this is my expression for the length of the path. And the thing that is unknown in this expression, well, there are two things that are unknown. I've got L is unknown, and y prime is unknown. So I've got a bit of a problem because I've got one equation, two unknowns. But we'll just tell you, spoiler alert. So what we're going to do is we're going to think about taking the derivative of L with respect to something. And we will want the case where it goes through a minimum, and at which point our dl with respect to that something will be a 0, and I'll get down to one equation, one unknown for y prime. So that's our goal, but we're not there right now. So the thing is that at this point we want to find, so what we want is y as a function of x for which such that L is a minimum. All right, so that's what we want to do, and I sort of gave you some hand-waving stuff about it, but we're going to put a pin in this example for just a moment and start thinking about another example. All right, this example is Fermat's principle. All right, so this is going to be a similar problem, except I'm trying to find the path that light can travel that will take the minimum amount of time. All right, so you'll see that there's a special case in which it reduces to the same problem as what we had in the first example, but in general it does not have to. All right, specifically if the index of refraction varies. So we should know that this was, so Fermat was obviously a French guy. This was pretty early on, so this is, he died in 1665, so it's kind of amazing that this came along as early as it did in terms of being sort of the same as Newton's work. But anyway, so and I wonder if that has, well, anyway, we'll move on, but this relates to an optics question. And he discovered that the path that light takes is always the path of least time. So, I guess we'll all right, so what this relates to is it relates to, let's say that you have an interface between two dielectric media. Let's say that you have a point A here and a point B here. And let's say we have an index of refraction up here of N1, index of refraction down here of N2. And as a result, you get a path for the light that looks something like that. All right, so in this case, what we want to think about is the time elapsed during this path to figure it out, what path the light will take. So let's go ahead and talk about the amount of time that it would take to travel ds. So I'm going to take a piece of this path right here and find the amount of time that it would take the light to travel that one little piece. I'll call that dt, which is the increment of time required to travel the infinitesimal path ds. All right, and that must be equal to the length of the infinitesimal bit of path divided by the speed of light at that location. And then we'll remember that the speed of light is equal to a constant divided by the index of refraction. All right. So in this case, the time it takes to travel the entire length, we'll use a capital T for that. So total time of travel. That's going to be the integral over the dt from, I should have said point 1 to point 2, but point A to point B, but your author actually uses 1 and 2, so I'll kind of mix it up here a little bit. All right, so, and then I can make my substitution for my expression above, 1 to 2 ds over v, which is equal to the integral from 1 to 2 of ds times index of refraction divided by c. C is a constant, it can come up front, 1 over c times the integral from 1 to 2 of the index of refraction. And remember, this index of refraction most generally can be a function of location times ds along my path. Okay. Now, in the case that index of refraction is a constant, it would come out front, and I would just have the integral over ds, which is the same thing that I had up here, and I get this exact same integral times something for my answer down below. But I'm going to go ahead and leave it here in its most general form. Okay. So, generally, I can make a substitution from above, though, so let me go ahead and do that. So, what I get is that t, my integral, is equal to 1 over c times the integral from point 1 to point 2, and then I need my index of refraction, times my ds, which I can go ahead and substitute from up here, the square root of 1 minus y prime of x squared dx. So again, now we know that if let's say that n as a function of location is known, we still have this total time of travel and this y prime of x are unknowns in this equation. I've got two equations, two unknowns. But since the path I'm looking for is one in which this time of travel is minimized, I could imagine maybe I could think about taking a derivative with respect to choice of path here. And then when I take that derivative, I could set it equal to 0 because I want a minimum. Then I would only have one thing as an unknown, and that thing would be y prime of x, from which I could find y of x. So again, this is a situation where I want to find y of x. For the case where my integral has the minimum value. All right? In theory, I hope mathematically we see we should be able to do that. But again, we're going to put a pin in it. So these are both kind of similar equations. I'll call this one star, I'll call this one double star. And we're putting pins in for right now until we're able to solve them. All right. So, things to remember. The condition for something to have a minimum or maximum value is for some sort of function. In this case, it is that t, it could have been the capital L as well, would be that dt with respect to something, we don't know what that is, let's call it A, is 0. And that the second derivative of t with respect to that something would be non-zero, really. Because if it were 0, then you would just be at a sort of a constant, right? Wouldn't it actually be a maximum or a minimum? Yes, Grant?
Are those partial derivatives or?
Yeah, they are. And I haven't even told you what the something is. But I mean, it's just in general, when we have something that we want to find is where it goes through max, like for instance, just y of x, or it goes through max, we take dy dx, and we want the derivative to be 0, but we want the second derivative to be non-zero. That's all. Okay. And we call these stationary points. Stationary meaning that that's a point where as you vary x, y doesn't change. Y stays at a stationary value at that location. All right. So what we need to do is find a path such that L and T are stationary. And I mean that respectively are stationary. In our expressions for them, so we've got in star and in double star. Okay, we need to find a case where those values are stationary. All right. And what are we going to vary? We're going to somehow vary path, which we will come up with a way to do that as well. And basically what we're going to do is we're going to construct from that need of making all these different paths and sort of having them be sort of a continuous function of paths, finding the path for which these are minimum and therefore stationary, and then finding the expression for that path. That's what we're going to learn to do, and this is called the calculus of variations. And it's basically going to, for our purposes, mean how integrals change by changing paths. So how varying paths change integrals is that. So varying the paths changes the intervals. That's what we're sort of studying. As a result, we're going to develop some ideas that are called variational methods. Those are the mathematical methods that are related to the calculus of variations. And we are also going to wind up with something called the Variational Principle. Which is really just a principle related to variational methods. An example of a variational principle would be Fermat's principle. So I think it's time for us to do it, and we're going to start with the Euler-Lagrange equation. All right, so we're going to learn how to solve that star and double star here, and then we'll actually solve it in the next section. All right, so I hope my goal before now was just that we kind of get the variational problem. All right, so hopefully we're there. And what we have is we have this thing that is an integral from x1 to x2 of something that is a function of path, which is y of x, of path's derivative, which is y prime of x, and also can be a function of x. And so that thing integrated over dx. I mean, this is basically, the f dx is basically just ds, all right? But we should note that we can express those as functions of y and x, or y will be a function of x, and it will also potentially depend on slope of y, as this one does. Okay. All right. So in general, this is the thing that we have. This is sort of our general form of a path integral from x1, y1 to x2, y2 along a path that is defined by y of x. Okay. So then what I want to do is I want to find, maybe that S is length, maybe that S is time, maybe that S is something else, but generally what I want to do is I want to find the path for which that S is a minimum value, is its minimum value. So I want to find the one y as a function of x function for which S is equal to its minimum value. Okay. So here's where we're going to start with that. We're going to consider, here's point 1, here's point 2. And maybe here is the path that has that minimum value. And here's a different path that is nearby. Okay, so this is going to be our path y of x, for which, so such that S is equal to its minimum. I've got this other path over here. It's a different path. So I need to give it a slightly different name. So I'm going to call it, use the capital Y for it. And it is going to be equal to y of x plus some function eta, which is also a function of x. I'm sorry that I made it go backwards. I didn't want that. Actually, that wasn't intended for my purpose. Let's just remember the verbal function. All right. So in that case, it must be, obviously eta at x1 must be equal to 0, as must eta at x2, because they still do go from the same initial to final point. Should that be my drawing, but it should. Okay, so that's my condition. And then I'm going to make a small change as well and say, you know what, maybe I want to, this is a fine condition, I'm going to stick with that, but I'm going to turn on this eta with something called alpha, with something that I can call alpha. So I'm going to sort of make a tweak to what I've done so far and redefine my other path. Capital Y is a function of x, where it's capital Y for that path, as the correct path, the one that has the minimum value of the interval I'm interested in, plus this eta x, which I've already talked about. But then I'm going to multiply it by alpha, all right, where alpha could go continuously from 0 to 1. Turn it all the way up. Okay. And in the case that I am close to that, my minimum in my integrand, alpha would be something small that I vary there, okay? Okay, so I'll just say where y of x now becomes equal to my actual minimizing function when alpha is equal to 0. So now I have that variable that's going to go through 0 when I'm at the thing that I want. Okay. So now I want to rewrite my general integral, which is right here. But I want it to have alpha in it because I want it to be a function of alpha, because alpha is the thing that I want to consider. So let's go ahead and I want alpha to be small, and I want the derivative of this with respect to alpha to be 0. So that's the variable that I want. So now I'm going to write the integral S as a function of alpha. All right, so what I've got is this integral from x1 to x2 from before, f y of x, y prime of x, x, dx. All right. Now, I'm going to make the change. I'm sorry. This would be my actual solution where it's the one that I want. So I should have this as a function of capital Y. Let me just rewrite that. We're going to get rid of that expression right there. Integral of x1 to x2. F of y of x, so that's a capital. Y prime of x, so that's a capital as well. And x. Yes, that's the expression I want. Okay. And then I can make my substitution from here, wherever I see my capital Y. So I have y plus alpha eta, my value of y, and then y prime meaning the derivative with respect to x of y, is going to be for capital Y, is going to be y prime plus alpha eta prime and x. Okay. Now, let's go ahead and note, because ultimately I'm going to want to think about the derivative of this object on the left-hand side with respect to alpha. And that's going to be equal to the integral of the derivative of my integrand, which is this function, with respect to alpha times dx. So let's think about the derivative of that integrand. I just want to do a partial here. So partial of f y plus alpha beta plus alpha beta prime and x d alpha. That's going to be something that's important to think about. All right. So what is that going to be equal to? Let's think for a moment. Let's say that f didn't depend on all three of these things. It only depended on the first one. In that case, I'd have df, where f is y plus alpha, a function of y plus alpha eta, with respect to the alpha. Okay. Then in that case, I would have, well, let's see. I'm going to think of this object as, this whole object in here as A. Just to call it something. So I'd have df, dA, times dA, d alpha. Okay. All right, so in that case, what do I get? I get, well, for dA, d alpha, I get an eta. And for df, dA, I basically just get, in the case that I'm exploring the region where alpha is small, which is the region I am exploring here. Right? So let alpha be small. Let's see, so. Let me see. Since I am trying to find that region where alpha is 0, when I'm close to that region, I will have df dA, where alpha is small, so that's basically just df dy, times dA d alpha, which is just eta. Are you guys okay with that? Okay. So in that case, for this derivative, I'm going to have to consider the derivative, I'm going to have three terms to think about. I'm going to have df d alpha, where I'm exploring this dependence on alpha, and I'm going to have another term where I'm exploring that variable's dependence on alpha, and then another one where I'm exploring that dependence on alpha. So I'd have df df dA d alpha plus df dB d alpha, where B is this object, plus df dx d alpha, where x doesn't depend on alpha, so that third term will be 0. Are you guys following any of that? Cool. So when I was making that argument, I was calling this object here A, this object here B. I'm going to go ahead and write that stuff out because I was going to skip it, but I'm not going to do now. Plus df dB dB d alpha plus df dx dx d alpha, which is 0. So this is sort of the aside there. All right, so what I get for df d alpha is this first term, which is df dy times eta, plus this second term here, which I'll allow you to show on your own time, is df dy prime, eta prime. All right. So, now, I need to keep you for one more minute because we're so close. So ds d alpha is equal to the integral from x1 to x2 of df dx df d alpha, pardon me, dx, that's what I wanted to say. All right, and I want that to be equal to 0, but I'm going to make a substitution here. Integral from x1 to x2 of df dy times eta plus df dy prime times eta prime. And I have to integrate that over dx. And that must be equal to 0. This is where we are now. All right? So this, what must this argument be equal to for that equality to hold? That's what we're going to pick up next time. But we are very, very close to having a Lagrange equation. So we'll finish this chapter next time. Look for something, and I'll fire you an email when the homework's assigned. We will finish this chapter next time, so please be reading.
Well,